Okay, this is the derivative of exponentials and logarithms. We've discussed these derivatives briefly, but the basic exponential e to the x is e to the x. It's wonderful. Or you'll see it as e to the u, e to the u du dx, which is essentially just use the chain rule. If it is not base e, some other base a, the constant a is a to the x ln x. For logarithms, the natural log, again the easy one, or you might see it as ln u, which is 1 over u du dx, which means that du dx, or whatever that derivative, goes on top. We're dealing with a log of a different base. There is an implication that these x's and u's are absolute values, or they're positive, because you cannot take the log of a negative number. So this is 1 over x times ln a. The ln a is on the bottom, and then there's the chain rule part. I guess if I did it as u du dx. Just gets multiplied by the end. And there are 4 of them. So my first question I'm asked is, at what point does the slope of the tangent line of this have a slope of 21? Well, the first thing I need to do is find the equation of the tangent line. So y prime equals 2 to the t ln 2 minus 1. So then I end up with, I'm asked, where does it equal 21? So where's y prime 21? I'm then going to solve this equation for t. I'll divide both sides by ln 2, giving me 21 over ln 2 equals 2 to the t. To undo this, I'm going to log both sides. Converted to logarithmic form, you set that into your calculator, you get 4.921. And this, for t, let's see, what did the question ask? It says, at what point? This is the t, or my x. I now need to get my y. One, and I plug it in, and this equals 27.3, roughly. My point, 4.92, 27.3. So that is my point. Point implies coordinates. Example 3 asks me, a line with slope m passes through the origin and is tangent to the graph y equals ln x. What is the value of m? So it's tangent, that means I need the equation for the tangent line. So I know that this is going to have points A, ln A. And the slope here is going to be 1 over A. And if I do the slope formula, this is one coordinate, the other one is 0, 0. So, good old slope formula, y2 minus y1 for x2 minus x1. So, that's m. M is also equal to 1 over A. At this point, A is my x coordinate. Y prime of A was simply 1 over A. So 1 over A equals, when I simplify this, I get ln A over A. Well, I can see the A's are on the bottom. I can multiply both sides by A and they'll cancel. I'll end up with 1 equals ln A. I could convert, and I'm going to end up with A equals E. I've got base E here. E to the first equals A. So E is the number for A. The slope of my at S, what is the value of M? M is here. M equals 1 over E. A little bit of a tricky problem having to use the slope formula and set it equal to the derivative. Example 4 asks us to do this. Along base A of A to the sine x. Well, I don't feel like going through the whole lot of work on this. Log base A of A to anything. This is equivalent. Before I take the derivative, I'm going to simplify to sine x. Do you remember that logarithms of a base and exponentials of that base are inverse functions? This is just cosine x. If you'd like to see it worked out with the chain rule, you can. Um, but it absolutely works without needing to be. You could, I guess, let's say we missed it. 1 over A to the sine x times ln of A times the derivative of A to the sine x is A to the sine x times cosine x, or A to the sine x ln A. That becomes over 1 times cosine x. All of that cancels and I'm left with cosine x either way. Example 5 focuses on something that's not actually an exponential function. We're going to find the derivative of this. That's not an exponential function. The variable is not x. That's my derivative. It's got another part with another similarly odd variable. 2 plus sine 3x to the pi. The derivative, bring the pi in front. Pi is a constant for an exponent. Subtract 1. Now I'm multiplying by the derivative of the inside. Derivative of 2 is 0. Derivative of sine 3x is cosine 3x. And I've got another chain there times it's got an inside of 3x, which has a derivative of 3. So I would simplify this to 3 pi cosine 3x times the quantity 2 plus sine 3x to the pi minus 1 power. We get a pretty simple one here for example 6, which is, and it says state the domain. Well, well, it says state the domain of f prime. First thing I'm going to do is take the derivative. Now, the domain of the function was 3 to infinity. Okay? The natural log has to have a positive number inside. The domain of this function would just be x is not equal 3, but if it was not in the domain of the original, it cannot be in the domain of the derivative. Okay, the derivative can only have a domain that was in the domain of the original function. The last thing we're going to do here is what's called logarithmic differentiation. And we're asked to find the derivative, which they're going to refer to as dy dx here, of this, x to the x. And we are told here that x is greater than 0. That's not exponential. It does have x as an exponent, but it has a x as the base as well. It's its own crazy thing. So the first thing I'm going to do is take the ln of both sides, which gives me natural log, and I'm choosing the natural log, not another logarithm, because it has the easier derivative. So I've just taken the natural log of both sides. As long as I do it to both sides of the equation, it's equivalent. I will then use my laws of logs to bring this exponent to the front. And I get ln y equals x ln x. I will now take the derivative of both sides using implicit. The derivative of ln y is 1 over y times dy dx. The derivative of x ln x, that's a product rule, 1 times ln x plus first times derivative of second, which this is going to simplify to ln x plus 1. I need to solve for dy dx like I do in all cases with implicit, which means I'm multiplying by y. Giving me just dy dx on the left side, and y, I'm not going to distribute it in here. I'm going to leave it factored out. Back in the original, I had y equals x to the x. I can't leave my y in here. So I'm going to substitute what y was equal to, x to the x, in for y, and this is my derivative. Logarithmic differentiation can come in handy in a lot of cases because it allows you to use those laws of logs. Okay, that is the end of section 3.9.